You know, our whole world runs on electricity, but have you ever really stopped to think about the massive, humming machines that make it all possible? Okay, let's dive into that. We're going to talk about the silent giants of the power grid, and more importantly, the invisible shield that protects them. Okay, take a look at this. This is a high voltage power transformer. And these things, they're the absolute backbone of our entire electrical system. Their job is to step voltage up or down so we can move power efficiently across the whole country. But here's the thing, they're incredibly complex, ridiculously expensive, and if one breaks, it can take months, sometimes even years, to fix or replace. So yeah, a failure here is not just some local problem, it's a real threat to the stability of the entire grid. So you gotta ask, right? How in the world do we protect something so vital? What is this invisible shield of technology that's standing guard, ready to react in milliseconds to stop a catastrophe? Well, that's exactly what we're gonna unpack. All right, first step, the heart of the grid. See, before we can get into the shield itself, we really need to understand what it's protecting. Let's zoom in on these assets, because they are, without a doubt, the heart of the grid. It's pretty simple when you think about it. Without these transformers, we just couldn't send power over long distances without losing a ton of energy. They're the absolute critical link in the chain. But, and this is a big but, because they're so huge and specialized, any failure is a massive headache. We're talking huge costs, major downtime, and that directly threatens the power getting to your home or to a business. So protecting them, it's not just a good idea, it's an absolute necessity. Okay, so if you're going to build a shield, you first have to know what kind of weapons are going to be thrown at it, right? So let's get into the anatomy of a failure. And wow, what a list it is. Inside these giant metal tanks, things can go wrong in so many spectacular ways. You could have short circuits between the miles of copper windings, insulation failing in the core, even a simple loose connection at a terminal can lead to a total disaster. The complex gear that changes voltage levels, yeah, that can fail too. And then you add in all the stress from the outside world, like lightning strikes or faults somewhere else on the grid, and what you have is a machine that's basically living under constant threat. So, with all those potential disasters, how do you possibly guard against them all at once? Well, the core idea is actually kind of beautiful in its simplicity. It all comes down to a principle of balance. This is probably the best way to wrap your head around it. Just imagine a building with really tight security. If 100 people walk in the front door, then exactly 100 people have to walk out the back door, right? If only 99 come out, security instantly knows someone's still inside, and something's not right. That is the exact same principle we use for electricity. Okay, so this principle has a name. It's called differential protection, or 87T if you're an engineer. Here's how it works. A special device, a relay, is constantly measuring the current flowing into the transformer and comparing it to the current flowing out. They should be perfectly balanced. What goes in must come out. If they're not balanced, if there's a difference, well, that means current is leaking out somewhere inside that transformer. And that can only mean one thing. There's a fault. But, just like any security system, there are ways to trick it. This simple, elegant principle of balance, well, it isn't always enough. Because sometimes the transformer itself is the one creating a false alarm. And this is where it gets really clever. Let's go back to that security analogy for a second. What if the building itself, for some reason, could just generate a harmless clone of a person that never leaves? The security system would go nuts. This is the challenge. Not every imbalance is a real destructive fault. Sometimes the transformer's normal operation creates an imbalance that's totally safe.
So here's the big dilemma. You've got two scenarios. On one hand, a really dangerous internal fault. On the other hand, a totally normal thing called magnetizing inrush. Now, inrush is just this huge temporary surge of current you get when you first power up a transformer, kind of like turning the key in your car. The problem? To a simple protection system, they both look like a massive internal problem. But the actions you need to take are complete opposites. For the fault, you have to trip the breaker immediately. For the inrush, you have to ignore it, or you'll cause a false outage. So, how does the shield tell the difference?
The answer, of course, was to make the shield smarter. Engineers came up with some seriously clever tricks to give the protection system the brains to tell a real enemy from a false alarm. And this makes it both super fast and super reliable.
Okay, the first trick is called harmonic blocking. The easiest way to get it is to think of it like sound analysis. A real fault has a very clean sound, a pure tone, right at the normal power frequency. But that magnetizing inrush, it has a really distinct, distorted sound. That distortion is made of other frequencies, which we call harmonics. And it turns out inrush current is packed with a specific one, the second harmonic. So the relay is basically programmed to listen for that specific distortion. If it hears that second harmonic, it says, that's just inrush, no big deal, and it blocks itself from tripping. But what happens if a fault is too quiet to hear? That's another challenge entirely. See, a transformer winding is connected to ground at one spot, called the neutral. And the weird thing is, the closer a fault happens to that neutral point, the less current it actually creates. It's like trying to hear a whisper next to a jet engine. Some of these faults can be so tiny that the main protection system, well, it might miss them completely. So for this job, you need to bring in a specialist. It's called Restricted Earth Fault Protection, or REF. Think of it like putting a super sensitive microphone right next to that vulnerable neutral point. It's a whole separate, dedicated system that's tuned to hear even the tiniest ground faults in that one specific zone. It's an absolutely crucial layer of backup. And the shield, it doesn't just stop with electrical measurements. Oh no. We also have physical and chemical defenses. First up, you've got the book holes relay. It's this really clever mechanical gadget that sits in the pipe full of transformer oil. If there's an arc inside that creates a sudden gas bubble or a surge of oil, this thing physically triggers an alarm or a trip. And then there's dissolved gas analysis, or DGA. This is literally like a blood test for the transformer. By taking a sample of the oil and analyzing the gases that have dissolved in it, engineers can spot slow-burning problems, we call them incipient faults, way before they turn into a catastrophic failure. So all of this, it brings us right to the future of protection. The whole philosophy is shifting now from just reacting to faults to actually predicting them before they can even happen. And you guessed it, this is where AI comes into the picture. Artificial intelligence is completely changing the game for that blood test, the DGA. Machine learning algorithms can chew through decades of gas data, finding tiny little patterns that no human could ever hope to spot. Then, deep learning models can classify the exact type and severity of a fault that's just starting to form, and with incredible accuracy. We're really moving into a world where we don't just protect the transformer anymore, we're actively managing its health. Okay, let's keep the lights on. Because when you take a step back and look at the whole picture, all this complex engineering, from a simple idea of balance all the way to advanced AI, it really all comes down to one single vital purpose. This invisible shield, this is the reason our power grid is as reliable as it is. This is what stops a single transformer failure from turning into a massive, cascading blackout. It really is the silent, unsung hero, working 24/7, keeping the heart of our electrical system beating strong and making sure the lights stay on for all of us. And that's really the path we're on. Which leaves us with one last thing to think about. As all this tech, the diagnostics, the AI, gets smarter and smarter, are we getting close to a future where a surprise transformer failure is just a thing of the past? Could we actually get to a point where we can predict every single fault before it ever happens? Well, the journey to build that ultimate invisible shield, it's definitely underway.